Hello everyone and welcome to our channel. My name is Gokul and today we are presenting our MSIC subject project, the reverse car parking sensor circuit. Have you ever been in a situation where you are reversing your car in a tight parking spot and you are just not sure how close you are to the wall behind you? Scratches, dents and minor collisions while parking are some of the most common problems drivers face every single day. And the solution everyday problem is exactly what we have built today. A reverse car parking sensor is a safety device that helps a driver understand how far or how close their vehicle is from an obstacle while reversing. It alerts the driver in real time using visual indicators, in our case, colored LEDs, and a buzzer alarm, so that the driver knows exactly when to stop. In this video, we are going to walk you through everything about this project. We'll start with how the circuit actually works in detail. Then we'll talk about the real world applications of this technology and finally wrap it up with our key takeaways. The circuit is built using basic and easily available electronic components: an IR sensor pair, op-amp ICs, potentiometers, resistors, LEDs, and a 9-volt battery. No microcontroller is needed. It's a pure analog circuit, which makes it a anyone studying electronics. So, without further delay, let me hand it over to Deepam, who will explain the complete working of this project in detail.
Thank you, Gokul. Hi everyone, I'm Deepam and I'll be explaining exactly how this reverse car parking center circuit works from the components to the logic. Let us first go through the components we use in this project. Three op-amp ICs, we are using LM741, which is a general purpose operational amplifier, an LDR light dependent resistor, which acts as our sensor simulating the detection. Three potentiometer RV1, RV2, and RV3, each of 10k ohms, used to set the reference voltage. A 10k resistor R1 used as a pull down in the sensor circuit. Three 1k resistor R2, R3, and R4 used to limit current to the output LED. A 150 ohm resistor R5 for the infrared transmitter diode. Three LEDs, red, yellow, and green to indicate distance. A diode D5 acting as an infrared receiver, and a 9-volt battery as the power supply. Now, let us see how the sensing works. The core of the system is the infrared transmitter receiver pair. The transmitter continuously emits infrared rays outward towards any obstacle behind the car. When these rays strike an obstacle, they reflect back to the infrared receiver. The closer the obstacle, the stronger the reflected signal, and the higher the voltage produced across the receiver. In our simulation, the LDR is used in place of the infrared receiver, and LDR's resistance decreases as more light falls on it. So it stimulates what an infrared receiver does. When an obstacle is very close, more infrared light is reflected, resistance drops, and voltage at the sensor output increases. The R1 of the resistor of 10k and the LDR forms a voltage divider. The output of this voltage divider, the varying voltage, is connected directly to the non-inverting input, pin number 3, of all the three op-amp comparators simultaneously. Now let us see the role of the op-amps. Each of the three op-amps is configured as a voltage comparator. The comparator does one simple job. It compares two voltages, the sensor voltage as at its non-inverting input and the reference voltage at its inverting input, and outputs high if the sensor voltage is greater or low if it is less. The three potentiometer RV1, RV2, and RV3 are connected at the inverting inputs of the U3, U1, and U2 respectively. By rotating this potentiometer, we manually set three different reference voltages representing three different distances. RV1 for U3 red LED set to a high reference around 6 volt triggers only when the car is very close, about 5 centimeter away. RV2 for U1 yellow LED set to a medium reference around 4 volt triggers when the car is about 10 centimeter away. RV3 for U2 green LED set to the lowest reference around 2 volt triggers first when the car is about 15 centimeter away. Now let us see the working by taking some distance scenario. Scenario 1. Distance greater than 15 centimeter. The obstacle is far away. Very little infrared light reflects back. The LDR has high resistance. The voltage at the non-inverting input is low, lower than all the three reference voltages. All three comparator output low. Result, no LED glow. The car is safe. Now, scenario 2, distance about 15 centimeter. The obstacle is getting closer. More IR light reflects. The LDR resistance drop. The sensor voltage rises and crosses the lowest threshold set by RV3. U2's outputs go high. Result, green LED close. Warning, you are getting close. Now, scenario 3, distance about 10 centimeter. The car moves even closer. Sensor voltage rises further and now also crosses RV2's threshold. U1's output goes high. Result, yellow LED glows. Caution, you are getting quite close. Scenario 4, distance about 5 centimeter. The car is very close to the obstacle. Sensor voltage is now high enough to cross even RV1's high threshold. U3 output goes high. Result, red LED and buzzer beeps. So, in summary, the system gives a progressive warning: green for safeish, yellow for caution, and red for stop immediately. Each LED is connected to its op-amp output through a 1K resistor to limit current and protect the LED. The entire circuit runs on a simple 9-volt battery, making it portable and self-contained. This is a simple yet effective analog circuit. No programming, no microcontroller, just pure electronics doing the job. Now, I'll be handing it over to Purvesh, who will tell you about the real-world application of this technology.
Thank you, Deepam. Hi everyone, I'm Purvesh and I will be covering the many real-world applications of the reverse car parking sensor because this small circuit has a huge impact in the real world. Industrial work vehicles and forklifts. In warehouses and factories, heavy vehicles like forklifts operate in narrow corridors. Proximity sensors based on this same pricing help prevent collisions with shelves, walls, and workers, improving workspace safety significantly. Another application is smart home automation. IR-based proximity sensors are used in automatic door systems, smart lighting that turns on when someone approaches, and security systems that detect intruders near entry points.
Start.
Assistive technology for differentially abled individuals. Proximity sensing circuits can be integrated into wheelchairs or walking aids to help differentially abled individuals avoid obstacles in their path, improving their independence and safety. Thank you so much, Gokul, and thank you, Deepam, for that brilliant explanation. So let's quickly summarize what we covered today. We built a reverse car parking sensor circuit using an IR sensor pair, three LM741 op-amp comparators, potentiometers, resistors, and three colored LEDs. The circuit detects how close an obstacle is and progressively lights up a green, then yellow, and finally a red LED with a buzzer as the distance decreases. Given the driver a clear real-time warning system. This project taught us some very important concepts in electronics: how op-amps work as comparators, how voltage dividers function, how IR sensors detect obstacles, and how we can combine simple components to solve real practical problems. The best part about this circuit is that it requires no programming whatsoever. It's a pure analog circuit that anything learning electronics can build and understand. We have discussed the applications of this technology and truly everywhere, from cars to robots to smart homes to factories. We hope this video was informative and helpful for everyone watching. Thank you.